So you've reached the time of your chemistry career where you've got to do a little bit more math, but we're going to be tying this in to the lesson on nuclear weapons. So in short, we've talked about how isotopes are atoms of the same element, only with different numbers of neutrons. Well, here's the deal. If you remember when we talked about nuclear fission and fusion, well, that is particularly with nuclear fission, the electrons cause this chain reaction. The neutrons cause this chain reaction, right? And so we're dealing with neutrons here. And so these tiny particles, even though they have no charge, so they just add mass, they still contribute a ton to the field of chemistry. So again, it's worthwhile studying the particle that is behind a lot of the chain reactions for nuclear weapons, right? Hey, an application for you. If you were to look on the periodic table, you're going to see three things on every elemental square. Obviously, in the center, you're going to see the element symbol. In this case, it's hydrogen. Somewhere on the top, you're going to see a number, and that's called the atomic number. That's the number of protons. Now, in the past, you might have been told that's the number of protons and electrons, but that's only true providing that you're not dealing with an ion. And in this class, you could very well be dealing with an ion. And so the atomic number is the number of protons. And on the bottom, and you're like, what's an ion? Well, just give me a few more units. On the bottom here is where you're going to see the mass of the element. But have you ever wondered why they don't just round 1.00797 to 1? And it's a very valid question. And I'm going to explain it to you again using the neutron. But again, remember that James Chadwick figured out the neutron was a thing by that weight issue. He was like, well, helium has got, double the protons of hydrogen. Why in the world does it weigh 4 times more if it only got 2 times the particles? Again, it's due to neutrons. So here's the deal, guys. No atom of hydrogen anywhere in the universe actually weighs 1.00797 atomic mass units, or AMUs. You're like, what? Let me explain. This number is a weighted average of the masses of every isotope of hydrogen. You're like, what? Well, let me remind you. In the previous slide, I showed you the 3 isotopes of hydrogen. Protium, that's got 1 proton and no neutron. So forgive me, I think in the previous video I misspoke. Deuterium has 1 proton and 1 neutron, and tritium has 1 proton and 2 neutrons. So you got no neutrons, 1 neutron, and 2 neutrons. And so what we do here is we average the weight of all 3 possible isotopes of hydrogen, and we factor in that calculation something called percent abundance. And I'll explain that in a minute. But for now, what I want you to understand, the atomic mass on the periodic table is just a weighted average of every possible isotope of that element. That is, how many neutrons can this element have? We're going to skip that other slide. And so here's an example. There we got carbon 12, we got carbon 13, and carbon 14, but this slide just looks at carbon 12 and carbon 13. Carbon 12 is an isotope of carbon. It weighs 12 AMUs, and its percent abundant is 99%. So that means that 99% of the carbon atoms in the entire universe is carbon 12. It's that particular isotope. Another possible isotope of carbon is carbon 13. However, only 1%, think about this, only 1% of every carbon atom in the universe is the isotope carbon-13. And so we take into account those percent abundances when we use this information to calculate the atomic weight on the periodic table. And so, we do this little calculation and we say, well, carbon-12 is 99% abundant. Therefore, the mass of carbon is going to be very, 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 very close to 12. But because we have some carbon, even though it's just 1%, that weighs above 12, the mass is going to have to slightly be above 12. So what I'm trying to say, the reason that carbon just doesn't weigh the whole number 12 on the periodic table is because you have 1% of all the other carbon atoms that weigh 13. And so, we don't average 12 and 13 because, we would only do that if this was 50% and this was 50%. But because carbon-12 is 99% abundant and carbon-13 is only 1% abundant, right? That 13 is not going to have much of an effect on the mass. And so we say that it weighs, 12.007 whatever. And so what I'm trying to get you to understand is the mass or the weight, whatever, on the periodic table represents the weighted average of all the isotopes. And so here's an example for you. Here's an element, the element LOL. It has two stable isotopes. The first isotope of element LOL is 5, and that's 80% abundant. So this here is an isotope, and it's 80% abundant. But you have another isotope of the element LOL. It's called LOL6. That's 20% abundant. And so I ask you to guess what in the world is the average atomic mass here. Well, here's the deal. The way you look at this is you're like, meh. Okay, so the first isotope, 5, is 80% abundant. That means this element is going to weigh something close to 5 AMUs. But the problem is, because the isotope LOL6, and obviously 6 is greater than 5, is 20% abundant, we're going to have to take that into account with the average atomic mass. But again, 80% of the element LOL weighs 5. And so the atomic mass is going to be very, 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 very close to 5. But because 20% of it weighs 6, we're going to have to say maybe it's more like 5.2 or 5.3 or something like that. So that's how you would, find the average atomic mass of an element. Now again, I know you can do all the calculations, that's in this slide, but I just want you to be able to estimate through understanding the concept. And so say that, this was not right here. Let me see if I can get a pen. Okay, it's not giving me a pen feature, but say this was LOL4 and it was 20% abundant. Well, the problem with that would be, since LOL5 is 80% abundant, if you said LOL4 was 20% abundant, the mass would actually have to be, maybe 4.8 or 4.9, because you would have 20% that weighed, less than 5. And so that's how you guess the average atomic mass on the periodic table. And so here's a few more problems. You can't work with a neighbor because you're kind of quarantined, but here's the deal. I'm dealing with boron here. Boron has two stable isotopes, boron 10 and boron 11. So without looking at a periodic table, I want you to guess what the average atomic mass would be, right? Well, the thing is, you're going to have to look up the percent abundant. So let's do that really quickly. Let's look at boron, stable isotopes of boron. And you can see here that boron 10 has a 20% abundance, and boron 11 has an 80% abundance. So here's the deal. Which one has the higher percent abundance? What's the boron 11? That means the average atomic mass is going to be very, very, very close to 11. But because 20% of all the boron atoms out there weigh 10, the average atomic mass is going to have to be slightly below 11. So if you look on the periodic table, boron weighs 10.81. So that takes into account 80% weighs 11, but 20% weighs 10. And so that's why the average atomic mass, if you look on the periodic table of boron, is like 10.8 or something like that. So let's go to the next example, copper. So we're going to look at the two stable isotopes of copper, copper 63 and copper 65, and estimate the average atomic mass. So let's go here and let's do that. Let's say stable isotopes of copper. And there should be a Wikipedia page on that. And so this said to take a look at copper 63 and copper 65. Well, which one's more abundant? It's copper 63. It is 69% abundant. Copper 65 closes the gap and is, about 31% abundant. So here's the deal. The mass is going to be much, much closer to 63. Much closer to 63 because, well, it's about 70% abundant. But because you've got about 31% that weighs more than 63, that means that the average atomic mass of copper will be a little bit of a number higher than 63. Again, because 69% weighs 63, but you got 31% that weighs a little more than 63. So that's why if you look on the periodic table, the average atomic mass of copper is 63.5. So what I want you to understand is that the masses of all the elements on the periodic table, by the way, this pttable.com, it's called the dynamic periodic table. Again, that's why you see the masses here. Or fine, let me be clear. I call this atomic mass, atomic weight, whatever. What it weighs is an average of the percent abundance of the isotopes for that particular element.